A developer's coding agent burned $12,000 in cloud bills overnight. A cursor agent running Claude wiped a car rental startup's entire production database, backups included, in 9 seconds. Claude Code ran terraform destroy on a stale state file and erased 2.5 years of course platform's data. No hacks, no bad models, just tools with too much permission and no one there to stop them. I've actually had a version of all three of these almost happen to me. And that's why I say the model isn't dangerous, it's the harness. Because between the model and the outside world, that is the real world, there is an entire software architecture, one that decides what tool exists, who can use them, when they can be called, how they're executed, what happens if they fail, whether the response is even trustworthy. This architecture is what I call the tool and guardrails layer. Last episode, we built the loop. The loop can think, but thinking isn't enough. Suppose I ask, what's the weather in Bengaluru or Austin or Mumbai? Can the model answer? Maybe. Can it guarantee it's correct? Maybe not. Weather changes every minute, right? The model has no live knowledge. It needs the capability. That capability is a tool. The tool actually extends beyond the training data. That is, it extends the capability of a model beyond its training data. Search, file system, terminal, database, email, Git, browser, MCP servers. Everything an agent can do is exposed through tools, which means without tools, an agent is simply an LLM wrapped inside a while loop, and we don't want that. Now, if you ask me what a tool is, and if I start explaining you, this is how a Python function looks like in a tool, that wouldn't make sense, right? Because that's implementation. You'd write that. You have frameworks and tools, probably open source harnesses for you to help do that. But that's not what we want. We want to understand if we were to build a harness of our own, that is the tool layer of our own, what would we need to know? And what I believe is these are the questions that you need to ask a tool. And the questions are, what is your name? What do you do? That is a description or detailed description of what the tool does. What arguments do you expect, which is the input schema? What permissions do you require? Can I retry you? Can I cache you? How expensive are you? What happens if you time out? Can you fail? Should a human approve execution? Every production framework converges towards the same abstraction. But I want you to basically give your attention or focus on this particular part. Notice how small this is compared to the harness around it, because this part is something that you own. You're a domain expert. You can write how the tool or what the tool does. Basically, if it's calling another API, if it has a bunch of sequence of steps that it needs to execute, or maybe it's an MCP server, a tool abstracted through an MCP server. Everything else exists so that the harness can safely use the tool or execute the tool. All of this. And if you want to build a solid harness, a solid tool layer, ensure your tool answers all of these for you. So go back. If you've already written MCP tools, go back and check and look at, basically create a checklist out of this and see if your tool is able to answer all of these questions for you. This is the most important diagram of today's video. I want you to, if you are a person who takes notes, I want you to draw it slowly. What we'll do is we'll basically go back to slide 1 and we'll use one of these issues or one of these incidents that happened with different companies and see what role they would have played or how they would have probably been exposed to the LLM and how one of those tools got executed, right? So let's use this one actually, the one with datatalks.club, right? So I'm going to go back here. Now, before I talk about the full tool lifecycle, I will walk you through each stage with the run underscore terraform example from datatalks.club, right? So in this particular stage, that is in the register stage, somewhere or one of the tools, or maybe the only tool, which is basically run underscore terraform, was executed at this stage. Let's call it, and if I have that here, so maybe here run underscore terraform was written, right? In the register stage, somebody has written it. Somebody has basically written a tool which has a method called run underscore terraform. That's it. Nothing has agreed to let anyone use it, which means it's still in the register state. So in the harness, in the register state, maybe in our case, in the our code example that we've had, there is something called as add tool, a method where you can add a tool to a list of tools. That is where the register happens. In one of the tools, there is a command called run underscore terraform, and still not exposed to the LLM. Now, in this particular state, which is a stage in that is in the advertise stage, the harness that you've written tells the model that this tool exists. You've added the tool to a tool list, and you're basically passing it to the tool as as context. You're telling this is the schema, and here's what the tool does, right? And if you go back to this, some of the attributes have been added, and most of the harnesses today, like LangGraph, LangChain, or Crew AI, these essentially allow you to write tool descriptions and names, right? So that's what has happened today. That's what has happened in this particular state. Advertise. In register, you register a tool which has a command run underscore terraform, and you're telling in this particular stage, you're telling the LLM model that this is a tool that you have access to, and this is a schema, and this is what it does. And still, the tool is still yet not advertised, meaning it is still not reachable at this stage also. Even a dangerous tool is harmless if the model never hears about it. But now the tool selection happens. Now the model looks at a task and it reaches for that particular tool. And the tool has a command called run underscore terraform. Remember, you have not made a decision. The developer who wrote this particular agent hasn't made a decision. Your script, you've not written a deterministic script, you've not written heuristics. That has not made a decision. It has a model. And this is a decision, right? It's not a guarantee. That's worth remembering before the next step. Before anything runs, check the arguments, right? And this probably stage didn't exist. Is the environment actually staging, right? Or did a state stale file just smuggle production through? This is where the disaster should have stopped it. Basically, I'm referring to this one, right? Because a state file had production footprint in it and it got wiped out, including the backups. Maybe if you had a tool lifecycle that looks something like this could have been prevented right here, right? That is, in the next one, there are two separate. Basically, remember in validation, I'm checking, is this valid for the environment that I'm running on? Should this be only run in staging or in production? I can probably have that check. In this particular state, that is in the permission check, there are actually two separate questions. And if I can go back to this particular slide, and if you can think about this particular issue, can the token execute the tool? Basically, that's authentication, right? And should it right now for this particular task, that's authorization. Pocket OS, that's the agent that Pocket OS ran, had a staging task and a production scope token. Nobody ever asked if they should be able to execute that. That means there were no permission checks. That's why it's so important to have a permission check in your tool lifecycle. In the next stage, which is probably the most important stage, this is where the execute bit happens. That is, this is where the tool is actually used. One thing that you could actually build is this particular execution sandboxed? Is it timed? Is it touching only what it needs to? That means it has access to an environment that it should be having access to. This is the only stage that actually does the work. In the next stage, that is in your tool lifecycle, ensure that you have an observed state, which tells you that did the tool execution actually succeed? Did it fail? Did it time out? Did it half finish? An agent that can't tell it if it failed or if it worked just keeps trying again and again until someone wakes up with a very very high cloud bill, and that's what happened in the incident one that we saw, right? $12,000 in cloud bill. You don't want that. You don't want that to happen, and you could actually prevent that if you have the right kind of observability, right? Now, the next step I want to talk about, normalize. For example, a 500 error, a stack trace, a none, an empty response from the tool. How do you basically manage that? The model doesn't want four shapes. It wants one. Normalize, just give it one. And the last one, the tool's job ends. When the when the tool's job ends, the loop's job continues, right? Because it is one request, but there are 9 different checkpoints. Only one of them touch the real world. Only one box actually runs code. Everything else is architecture. Let me go back to the original slide. There's a reason we are calling this particular layer, that is layer 2, tools and permissions. And the reason we say this is because guardrails, essentially that manage permissions, aren't a separate system. Uh, you know, Guardrails are actually bolted alongside the lifecycle. And if I go back to the lifecycle, guardrails are essentially part of this particular lifecycle itself. They are policy checks inside specific stages, though, and that's something that we'll actually shed some light on now. If you look at this, and this is basically the same stages here, but we've clubbed a few, and we'll see where actually the guardrails fit in, different types of guardrails, that is, right? And then you'll understand why this particular layer is called a tools and guardrail layer, right? So for the register and advertise stage, the stage where you essentially register an agent, register a tool, and advertise the tool, basically tell the LLM as part of a prompt through context what tools it has access to. It could be, for LLMs or frameworks which take a tool as a different argument. Even then, you are essentially, you know, that particular step also belongs to the register and advertise stage, right? And in this particular stage, you check or you bring in the input guardrail. And in this stage, you tell or you ask, is this tool sane to expose? Now, if you go back to the previous one, there is a tool that I'm actually exposing to the LLM, which has a command called run underscore terraform, or maybe it has the name itself of the tool is run underscore terraform, right? Should that tool be exposed to the LLM or through the LLM, uh, right? This is basically the guardrail that should have been used. And in the next one, basically, when the model is essentially selecting the tool, you can actually introduce a selection guardrail. And can this tool be called here is something that you can actually use. And this could be part of the output. You basically append it as part of your harness to the output of that particular LLM call. If the LLM has selected this particular tool, you then run a selection guardrail. Given the context, given the prompt, should this tool be even used? That could be probably introduced, right? The next one is basically the permission check, permission guardrail essentially. Uh, should this user even get it, right? Should this tool be even exposed to this particular user actually? Uh, in the execute stage, that you can introduce an execution guardrail, and this is where you basically bring in is this particular execution or this particular tool being executed in a sandbox? Are there rate limits to it? Do you need a human approval to actually, even before you check all of this, do you even need a human approval or a human in the loop to even execute that? Do you need a permission? That's something that you can actually check or have guardrails around. And in the response bit, you also check all of these, right? PII, secrets, toxicity, compliance, sensitive information. You're ensuring that all of this is basically not part of the response that the LLM is generating, and you don't want that response, either exposed back to the user or that goes back to the LLM again and essentially corrupts the context. So you want to ensure that there are guardrails at different stages of the tool lifecycle, and you have essentially added these guardrails at the right stage so that you are protecting uh, the agent from either selecting the wrong tool or you exposing an incorrect tool to the LLM. And even if for some reason the tool has essentially made it to the execution stage, then you check, should a human then actually approve the execution of this particular tool. All of this can be managed if you have the right guardrails at the right stages of your tool lifecycle. So very important you understand, one, the tool lifecycle and different guardrails that you can introduce in the tool lifecycle. This could mean different for you in your workflows, but the idea here is if you're building a harness to solve any kind of business problem, uh, basically build an agent for a specific business problem. That means you're building a harness very specific to your enterprise needs. You ensure that you're also bringing in these kind of guardrails into your tool lifecycle, actually. This is one important concept to understand, especially when you're basically building uh, harnesses around your tool calling or harnesses around the tool, right? Basically the layer two, the tools and guardrails layer. Uh, when it comes to static registration of the tool, you are in full control of what that tool is. You write the right names, the right description. Essentially, you're following the best practices of writing what a tool is, and and let's ensure that you followed a checklist of writing what this tool is. It answers all of these questions really well for you. It does because you are in control of what the tool is. It's part of probably natively built into your agent system. However, there are going to be scenarios, a lot of them in an enterprise setup, where you're working with an MCP server, essentially a server that is exposing a lot of tools, which you probably don't even own. So you don't know how the name is written, the description is written, whether the input and the output is clearly defined as part of the metadata of the tool, right? So this is one important consideration that you need to keep in mind, and that could break the pattern, basically the life cycle itself here. And this is where we strongly recommend that you basically bring in the permission check, because this is going to become the most important guardrail for you, especially if you do not have full control over what or how the tool is basically designed, keeping all the best practices in mind. So ensure that you have that one important check, which is basically the permission check, that you can bring in, and you the tool that you're executing, you know that the user has absolute right to execute that particular tool. Right. So what are the principle of good tool design? And the first one actually reminds me of the solid principles. One tool, one responsibility. Your tool should be able to do one thing and one thing really well. That's it. The next one is basically write descriptions for the model, not for humans, meaning the model is the only reader that matters at call time. So ensure that when you're writing the description you're writing for the model, you can be discreet and not be overly verbose. But the idea here is still that ensure that while you understand what the description is, when you look at it, you also are writing it for the model and not for a human. Structured input and output, always JSON, never free text. I think that goes without saying. All tool calls should have a very structured input and output. And this is coming from a lot of experience of writing tools. Uh, Never swallow an exception, meaning a tool that fails silently teaches the model the wrong lessons about what worked. So ensure that you have very explicit failures. The next one is idempotent wherever possible. You want to ensure that a retry doesn't, for example, double book a fight, right? You want to ensure that it is idempotent. The last part, and this is something that you'll probably, uh, you know, hear, or you'll probably never hear from people, but this is actually, you know, maybe a lot of people, would avoid to say this, but this is a little bit of contrarian, right? And it might look, you know, opposite to what I just called out in the beginning, especially the first and the second one, right? If you have more than 15 tools, ensure that you have fewer tools and they are coarser from there, meaning that beyond 15 tools, you should pick tools that are doing multiple tasks or are doing multitasking essentially. And the reason for that is the tool descriptions, and especially the tool descriptions, right, with the schema and everything, eat into the context and the attention. And a very narrow tool degrades selection accuracy faster than maybe a smaller set of well-designed multitask or multi-purpose tools. So composability is a good instinct at 5 tools, but at 30, it's the reason that the model is actually picking the wrong tool. So ensure that beyond 15 tools, you're actually picking only the ones that are multitasking. Otherwise, ensure that somehow you're reducing the number of tools that you're exposing to the LLM. Production harness engineering begins not at does the tool actually work, right? But at what happens when the first time it doesn't work. Meaning, every mature harness protects against a wrong tool that is selected, wrong arguments, meaning that you need to have failure modes for these kind of scenarios. Hallucinated tool that is actually generated by an LLM, incorrect tool that is generated by an LLM. Repeated calls, you don't want the tool call to happen several times, which means that you also want to ensure that there is no infinite retry. A slow tool, for example, if the tool is actually calling an API or another service, or, over a remote connection, you want to ensure that the latency is not beyond the permissible threshold. Network failure, again, it's right back to a tool call that you're making over a network. Permission denied, I mean, it goes without saying. Malformed output, you need to have a failure mode to essentially handle a malformed output. Timeout, again, is basically tied back to this. Duplicate execution, we come back here. We don't want repeated calls happening back to the same tool. You want to ensure that the tool is always executed only once. And partial success, you want to ensure that you're handling the partial success of a tool, and there is a graceful way to basically manage outputs like this from a tool. That is all right. Now let's put everything that we've learned in today's video in this particular architecture, the final architecture slide, right? We have a user. The user essentially sends a prompt, sends a query to your agent harness. There is a loop essentially has access to a tool registry. It adds all of that and sends that as context to the LLM. This is where the selection happens. The LLM has selected a tool, and then we've written validations and permissions. Basically, we've added guardrails in this particular stage. We probably also have guardrails here previously where the tool is being selected, but essentially the validation permission happens here. The execution happens in this state. Basically, the tool has been validated, the permissions have been vetted, and the tool call is being made. Then the observation of the output of the tool happens. If you look at the failure mode is basically tied to the observation. Some of them is basically tied to the observation of the output of the tool. Normalization, again, you want the output to be fed back to the LLM again in a specific, easy to consume format, right? This is where the loop is called. And it continues iteration. The iterations happen several times until the loop is exited, and a response is sent back. I wanted to basically notice something here. There is no mention of what a tool is. We're not showing what the tool looks like. The tool itself occupies almost no space in this particular diagram. The architecture around the tool occupies everything, and that's harness engineering. Everything here is harness engineering. In the previous episode, we built the brain. Today, we build the hands. And before you stop this video or jump to the next one, I want you to find your riskiest tool from the tools that you probably built for your agents. The one with delete and deploy, essentially. Go find a tool with delete and deploy or destroy in its name. And I want you to walk it through basically the tool that you've written through these 9 boxes. And if any of the box is empty, that's the fix for you tonight. Don't postpone it to the next quarter. Fix it today. In the previous episode, we built the brain. Today, we built the hands. But before you basically close this particular window or move on to the next video, I want you to go and find your riskiest tool. Probably the one which has the word delete, deploy, or destroy in its name, and walk it through these 9 boxes that you're seeing on the screen. If any box is empty, that's tonight's fix. You should be fixing that tonight, not next quarter. Because as you saw, how important layer 2 is, the brain is good, but hands alone aren't enough. I want you to imagine that your agent can actually think and act, right? So far that we've established that. But it remembers nothing at this point in time because at every iteration, it starts from scratch. That's exactly what happens without layer 3. In the next episode, we build what I believe is the most misunderstood layer in modern AI systems. Not RAG, not vector databases, not memory. We'll build layer 3, that is context engineering. Because context is the operating system of every AI agent. If you haven't subscribed to this channel, please like and subscribe. I'm hoping this was useful. Until next time, see you then.